look at some special triangles which allow us to figure out certain sine, cos, and tangent without a calculator. Here is the first special triangle. You draw a 90-degree triangle where this side and this side are the same. That makes it an isosceles triangle. If those two sides are the same, then this angle and this angle are the same. Would you agree? That's what an isosceles triangle is. Now we can make this triangle as big or as small as we like, as long as this side and this side are the same. So I'm going to pick 1. I could pick 2, I could pick 3. It actually wouldn't matter what number I picked. Then this side would be 1. And a squared plus b squared equals c squared would make this side square root of 2. And you can now do sine of 45 degrees without a calculator. Because sine of 45 degrees is opposite over hypotenuse, which of course we would have to rationalize our denominator. And you would get root 2 over 2. Check out our calculator. We did sine of 45. Now, if I write the square root of 2 divided by 2, I get that 0.707, same number as I did when I typed in sine of 45 into my calculator. So because of this special triangle, now anything with 45 degrees can now be on a non-calculator part of a test or a quiz. Because you can also do cos of 45 degrees adjacent over hypotenuse, which of course we have to rationalize the denominator, is also root 2 over 2. And tan of 45 is the easiest one to do without a calculator. It's going to be 1 over 1, opposite over adjacent, which is, of course, just 1. Check it out on our calculator. If I do tan of 45 degrees, I get 1. And not only do you have to do sine, cos, and tan of 45 degrees, you can now, without a calculator, do any angle that has a reference angle of 45 degrees. So for example, let's think here. If I drew a reference angle of 45 degrees in quadrant 2, what is the angle in standard position? Be 135 degrees. So I'm saying now without a calculator, you should be able to tell me what sine of 135 degrees is. Any guesses? And cos of 135 degrees, and tan of 135 degrees. And we'll check if we're right. If 45 degrees for sine is root 2 over 2, then sine of 135 degrees is root 2 over 2. If cos of 45 degrees is root 2 over 2, then cos of 135 degrees is negative root 2 over 2. Our CAST rule is coming into play here. We're looking in quadrant 2. And what will tan of 135 degrees be? A negative 1. Same as tan of 45. But the CAST rule says it's negative. Sure enough, let's just check. Tan 135. Yes, negative 1.
the one for the type.
Why is it the same as these ones? Because if I drew a triangle using my reference angle, it would make this exact same triangle.
Okay.
So it's all based on the triangle with the reference angle, is what sine, cos, and tan are once the angle gets bigger than 90 degrees.
Okay. Okay, so if whatever you're looking at is, let's say, 260 degrees, then...
Here, well, let's use 225. Here's 225 degrees. If I have 225 degrees, I can make a triangle back to my nearest x-axis,
45.
and this will be 45 degrees, which is the same as this one. So you have, on page 444, right, they have 45 degrees, and they have root 2 over 2, root 2 over 2, and 1. Once we get to 135 degrees, we have negative root 2 over 2, sine is still positive at root 2 over 2, and tangent was negative 1. If we went to 225 degrees, which one? For 225, that's going to be in quadrant 3. These numbers are going to be the same, except this time only the tangent is positive. And when we get to quadrant 4, the numbers will be the same, but now only cosine is the positive. This is special triangle number 1. Okay? Special triangle number 2. I'm going to draw this triangle. What's the other angle in this triangle? 60 degrees. Do you know what kind of triangle this is? Equilateral. So all the sides are the same. What's the problem with the equilateral triangle? You cannot use SOHCAHTOA. You can only use SOHCAHTOA with a 90-degree triangle. So what do I do with this one? I decide to cut it in half. I make 90 degrees down here. If I cut it in half, would you agree this makes this 30 and this 30? Now all the sides are the same. Oh, before, you know how I said it didn't matter what sides you pick? That these should work out to the same thing? Okay, I just want to show you that if you had picked 3, then this side would be 3. Can you see that tan is still going to be 1? But this time you get 3 divided by 3. And if you did a squared, which is 9, plus b squared, which is 9, you would get the square root of 18, which happens to be 3 root 2. And can you see that if you did opposite divided by hypotenuse, you'd have 3 over 3 root 2. Your 3's would cancel out. It's still 1 over root 2. It's exactly the same number. So it doesn't matter which numbers we pick for the sides. A squared plus b squared is equals c squared would still be able to figure out. But sometimes we choose numbers, like we chose 1, so our mental math was easier. Much better than choosing, say, 153. I wouldn't recommend it for a squared plus b squared equals c squared. Same thing here. We get to choose all 3 sides have to be the same. I'm going to choose 2. Why is 2 a good number? Because then when I cut this in half, can you see that both of those would be 1 and 1? And this would still be 2. And now we have to do a squared plus b squared equals c squared. And we'll get the square root of 3. And And so now we can do sine of 30 degrees, cos of 30 degrees, and tan of 30 degrees without our calculator. Sine of 60 degrees, cos of 60 degrees, and tan of 60 degrees. We can do all of these without our calculator. Because if I go to 30 degrees, SOHCAHTOA, sine says it's opposite over hypotenuse. That's 1/2. Cos of 30 degrees, adjacent over hypotenuse. That's √3/2. And tan of 30 degrees, opposite over adjacent, 1/√3, of course. We have to rationalize our denominator, so we get √3/3. And sine of 60, opposite over hypotenuse. Cos of 60, opposite over hypotenuse. Tan of 60, opposite over adjacent. And not only do you know those, but we can figure out anything that has those as reference angles, which they've got as part of the chart in example 2. I'm going to show you that chart in example 2. So on page 445, they did 60 degrees. 120 has a reference angle of 60 degrees. Maybe we just write that underneath. 240 has a reference angle of 60 degrees, and 300 has a reference angle of 60 degrees. And so based on this, right, if you wanted to find cos of 120, it's also going to be 1/2, but according to our CAST rule, 120 degrees is in quadrant 2. Notice that only the sine one is positive. They were all positive in quadrant 1. In quadrant 2, only sine was positive. In quadrant 3, only the tangent was positive. And in quadrant 4, only the cosine was positive. So we have so far 4 angles with 45, 4 angles with 30, 4 angles with 60. You now have 12 angles that you can do without a calculator. How did I get the? Yeah, go back to the triangles. How did I get the square root of 3? The 30. They were all 60, and then I cut it in 1/2. So if I take a 60 degree and I cut it perfectly in 1/2, I get 30 and 30. And that also made the bottom, instead of the whole bottom being 2, now it's cut perfectly in 1/2. It's 1 and 1. So one of the things that they noticed that when you make a triangle, you have an x coordinate, a y coordinate, and your radius. Or as the hypotenuse they label as r, because if you put all those points all together, it would make a perfect circle. And this is your reference angle right here. And a pattern shows up that cos is the adjacent over whatever your hypotenuse is. So it'll be x over r, sine will be y over r, and tan is y over x. And what that allows us to do is it also allows us to figure out the following chart. that if you had angles of 0 degrees, 90 degrees, 180 degrees, and 270 degrees, even though you cannot make a triangle with your reference angle anymore, because your reference angle is 90 degrees, if you try to make another 90-degree angle, you're already only have a straight line. But despite this, we can still figure out cos of 0, sine of 0, and tan of 0. Cos of 90, sine of 90, and tan of 90. If we imagined a triangle, even though it's impossible to draw. So these are another 4 angles that we need to know without a calculator. So if I had, this is a triangle with 0 degrees there, a 90 degree here, and another 0 degree there.
Where's the 90?
You can't see it because it's a flat line. It's very confusing. Okay? I will draw it like a triangle, like this, and I will say this is 0 degrees. That makes no sense, but I'll pretend it does. If this is 0 degrees, would you agree that they'd be completely flat? I've drawn it poorly, not to scale. How tall is this side? 0.
Wait.
Okay?
Okay.
If it's completely flat and that's 0, and this side is 1, and it's completely flat, how long is this side? 1.
How do you know that side is there?
Because it's flat. This side and this side, if it's completely flat, is like,
No.
there's my triangle,
The first one.
which isn't a triangle.
Where did you get
It's just confusing.
Where did you get the one at the bottom?
It could be 4.
Oh, okay.
It doesn't matter. However big or however long, I could choose whatever number, just like the other ones.
Okay.
I just chose 1. So what is sine of 0? Opposite over hypotenuse. 0. What is cos? 1 over 1. 1. What is tangent? 0 over 1. Yes.
So when you're doing 380 degrees, the reference angle is also
0. It's the same triangle flipped around. This one's fun. Let's do the 90-degree one. Okay? This is 90 degrees. This is 90 degrees. Not drawn to scale. What is this angle up top? 0. Because it has to add up to 180. Well, that makes no sense. My scale is bad. How long is this side? If this angle is 0, this side has to be 0. This is this one right up here.
Where did you get the second 90 from?
Because I'm using this red angle of 90 degrees.
And the other one is
And I'm drawing a triangle back to my nearest x-axis, but it's really, this is not allowed to draw a triangle this way. This is making it not to scale. Now, if this side was 2, this side would have to be 2 as well. It's not really a triangle, but now I can still do trigonometry with it. What is sine of 90 degrees? The opposite side over my hypotenuse. 2 over 2. Sine of 90 degrees is 1. So we're I'm showing you with triangles that don't actually exist, but it still works as the idea. If you type into your calculator, you cannot draw a 90-degree triangle with one of the angles being 90, the other one's 0. It's not really a triangle. But the mathematics still works. Sine of 90 degrees is 1. We have a problem with tangent of 90 degrees. Because tangent of 90 degrees would be the opposite side, which is 2, over the adjacent side, which is 0. And 2 divided by 0 is not allowed. So sure enough, tangent of 90 degrees is not allowed. You type it into your calculator, it gets mad at you. Don't do that. error. Right? Value entered is not allowed. So, it's not very happy. Then it gives you some really complicated e to the exponent of pi over 2 times the imaginary number. It's like really confusing there. So it's like definitely not allowed. So these are other values that we have. And so when we get to example 2, they want you to find sine cos tan of 30 degrees, 150 degrees. Sine of 30, cos of 30, and tan of 30. These would all be in quadrant 1. Well, from our special triangle, so if you look at 30 degrees on that equilateral triangle that we cut in half, opposite over adjacent, that would be 1 over root 2. Cos was root 3 over 2. And tan was root 3 over 3. In quadrant 2, what angle has a reference angle of 30 degrees in quadrant 2? 100 and? Right? Because if you think about, here it is in quadrant 2, it has a reference angle of 30 degrees. Does it make sense that this has to be 150? And so I can now do sine, cos, and tan without a calculator of 150. Sine will be 1/2. According to my cast rule, sine should be the only one that's positive. Cos will be negative root 3 over 2. And tangent will be negative root 3 over 3. Once I get to quadrant 3, what angle in quadrant 3 has a reference angle of 30 degrees? It's 200 and something. 210, because you would go 180 and add 30 more. And now we can do all of these without our calculator. But according to my cast rule, they're all going to be negative except for tangent. So sine is now negative 1/2. Cosine is negative root 3 over 2. And tangent is positive root 3 over 3. And finally, in quadrant 4, what angle in quadrant 4 has a reference angle of 30 degrees? 330 degrees. And so in quadrant 4, cos will be the only one positive, so sine will be negative 1/2. Cos will be positive root 3 over 2, and tan will be negative root 3 over 3. Just to double check this on my calculator, I'm going to type in sine of 330. Well, I have to quit first. Sine of 330. Do I get negative 0.5? I do. So with those two special triangles, you now have 12 things you can do without your calculator for sine, cos, and tangent.
Why is it different country?
If I go to quadrant 4 and I draw a reference angle of 30 degrees to my nearest x-axis, and I want to figure out what this angle in standard position is, I have to figure out this all the way around is 360, right? So 330 plus 30 makes 360. No, it's always to the nearest x-axis. So it's sometimes, I find This question, if you want to know a question that people get wrong, this is one that people often get wrong. They give you this angle right here of 275 degrees. And they say, what's the reference angle? It's only 5 degrees away here. It's so tempting. You're so close to your y-axis. You're like, I want to say 5 degrees. But no, the reference angle is 85 degrees. It's always to the nearest x-axis. But guaranteed, as soon as it gets close to the y-axis, you're going to be like, oh, but wouldn't it be nice just to go to the nearest x? Like, it's so much closer. And there's less mental math. Come on, please. No. It's always to the nearest x-axis, so your reference angle is bigger. Oh. That's what I mean, it's a full lesson. We've only done example 2 of 4 examples already. Okay. Question number 9 to circle on this one.